Welcome to Calculus. Today we will investigate finding equations of tangent and normal lines to given functions at certain points, focusing on the limiting process as a strategy for finding tangent and normal slopes. We'll take a look at two examples, one where we write the equation of a tangent line, the second where we write the equation of a normal line. To begin, we need to decide how we're going to find the slope of a tangent line to a curve at a given point. So what we'll do is take a look at some generalized example here at the beginning, and then we'll apply it to our two examples. So we'll start with a graph of a arbitrary curve, a function here on the coordinate plane. And what we'll imagine is that we've got a function, so this will be some kind of, I don't know, a quadratic, some kind of even polynomial function. And we'll imagine that it has passing through it a line at two separate points. So we'll define this as a secant line. Remember from geometry, a line that crosses a curve at 2 points is defined as a secant. So I'll label it so. And to catch the idea of slope here, what I want to do is define those 2 points, but we'll do it generally. So this point on the right side, I'm going to trace down to the x-axis, and we'll call that point simply x. That's the x coordinate of that point. The y coordinate, if I trace over to the y-axis, we can call f at x. So again, we're not trying to put numbers on this, we're just looking at it algebraically. There on the left, if I trace down to the x-axis, this point on the left I want to define as C. And that's in a way a fixed point on the graph. If I find its y value by tracing over to the y-axis, we could say that that is f at C. So let's define the slope of the secant in terms of those 2 points and the way that we've labeled them. So the slope of the secant line, remember from algebra 1, it's really the change in y over the change in x, delta y over delta x. And then specifically here for us, it's going to be f at x, which is the y value of the upper point, minus f at c, which is the y value of that lower left-hand point, over x minus c, and that would be the change horizontally. So we know just from the basis of how we define slope in algebra 1 that that would give us the slope of the secant line. But what we're really interested in is not the slope of the secant line, which crosses the graph in 2 points, but really the slope of the tangent line. So we need to remember tangent line geometrically is a line that crosses the graph in 1 point. So we've got to imagine that we're taking this secant line that we've sketched, and we're going to let x travel over towards C, which really will bring f at x closer and closer to f at c. And as we go, we're headed towards this line, that green line, which is now intersecting the curve in just 1 point, and we can then identify that as the tangent line. The question is then, how do I write its slope? So the slope of the tangent line, if we think of the way that we brought that x value and let it approach C from the right-hand side, and in the same way it brought the f of x value towards the f at c value, that's really a limiting process. So the way that we define the slope of the tangent line is the limit as x approaches C of this slope fraction. And it's the same one we used up here for the slope of the secant. So it'll be f at x minus f at c over x minus c. And that is really our definition for the slope of a tangent line at a certain point. It's such an important definition in calculus that we give it a special notation a lot of times we call this f prime at c. So I'm going to circle that just to indicate that that's really our go-to equation to calculate the slope of the tangent line. And then once we can catch that, we'll use our Algebra 1 strategies. I'm using the point slope form to actually write the equation of the tangent line. So I'm going to take that circled green equation and I want to apply it to our first example. So here's number 1. We want to calculate the slope of the tangent line at the given point. And then we want to write the slope-intercept equation of the line tangent to the function at the given point. And then to check our work and to visualize this arrangement, a function with its tangent line at a given point, we want to graph both the function and the tangent line here on the coordinate plane. So let's start by calculating the slope of the tangent line. So recall we'd called that f at c. I'm sorry, f prime at c. But before we do that, I just identify some parts here. The equation itself is f at x. So what is labeled here as y is our f at x. The c value is going to be -1, and f at c is that specific value of 2. We could have calculated that too if we took -1 and plugged it into that quadratic. But that point's already given to us, so we don't have to. So we are ready to set up our slope of the tangent line. So we are calculating f prime at -1. Again, this is the slope of the tangent line at the x value of -1. So that is the limit as x approaches, that would have been c, so I'm going to substitute in -1, of this fraction. So f at x here is -2x squared plus 4 minus f at c, which we saw was simply 2, and that's over x minus c, and again c is itself is just -1. So there's our setup with this specific function at this given point that's on the function. So what we want to do now is we want to use our limiting strategies in order to simplify this limit. So I'm going to start by letting these parentheses go in the numerator. So this is again the limit as x approaches -1 of -2x squared plus 4 minus 2. So I see that the 4 minus 2 is going to give me a difference of 2. So this numerator is now -2x squared plus 2. And the denominator, the double negative would become a positive, so that's x plus 1. So at that point, we could try direct substitution, but really the way we've set it up, I see that I'd have an indeterminate form. If I plugged in -1 for x, in the denominator, -1 plus 1 is 0. That's undefined. In the numerator, -1 squared is 1. 1 times -2 is -2, plus 2 is 0. So direct substitution would give the indeterminate form 0 over 0. So we'll hold off on direct substitution, and we need to use some algebraic strategies because we can't find the limit from the indeterminate form. So what I want to do is factor the numerator. So this equals, again, the limit as x approaches -1. And I see that I've got a constant coefficient term of 2, so I'm going to factor out, in fact, -2. And what that would leave me is x squared minus 1. And as I take a look at that quadratic that I've got in the numerator now, that is the difference of two squares pattern. So I recall from Algebra 1, Algebra 2, that I can factor that using that difference of squares patterning, -2 times x plus 1 times x minus 1. And I've factored that quadratic, that difference of two squares. At that point, I'm looking for a cancellation between my numerator terms and denominator terms, and I see that I've got x plus 1 in both numerator denominator, so that will cancel. And this gives me now the limit as x approaches negative 1. Now of just a single level, so this is now a linear expression, negative 2 times parentheses x minus 1. And since I got rid of that term that was causing the indeterminate form by direct substitution, now I can use direct substitution to evaluate the limit. So I'm going to drop the limit notation. That becomes negative 2 times specifically the x value negative 1 minus 1. And that would become negative 2 times negative 1 minus 1 is negative 2. Negative 2 times itself is 4. So it turns out that the slope of the tangent line at negative 1, 2 is 4. So at that point, what we want to do is we want to write the equation in point slope form. So we'll do that here. Notice how this question has multiple stages. We go for the slope of the tangent line first using this definition of the slope of the tangent line, that limiting process. And here we're switching gears to write the point slope equation of the tangent line. So I'm going to bring the pieces we need for that. Remember, the form itself is y minus y1 equals m times x minus x1. That form came from the definition of slope. And the pieces we're going to fill in are 3. We're going to put m, so we've already decided our m is 4. And then I need an x1, y1. I need a specific pair of values. And those are, if you can remember, my c and f of c. So the x value there will go for x1, negative 1, and the f at c value will go for y1. And then I just need to fill in the parts that remain variable. So y minus 2 equals 4 times x minus negative 1. Now I'm ready to simplify it. I want to end up graphing this line, so I need to put it in slope-intercept form, which is y equals mx plus b. So I'm going to simplify this equation. So it becomes y minus 2 on the left equals 4 times, in parentheses, x plus 1. I'm going to distribute the 4. So this now becomes y minus 2 equals 4x plus 4. And then the only term left to move is this minus 2 from the left. I'm going to add it over. And that gets me the equation of the tangent line at the point negative 1, 2. It's y equals 4x plus 6. And that's really a big part of this question, is generating that equation. Now, to check that this all works geometrically, I want to graph both the original function f of x, which is negative 2x squared plus 4, as well as our tangent line, which is y equals 4x plus 6, on the coordinate plane. So I'm instructed here in the directions to do so by creating a table of points. And that's how we'll approach graphing f of x. So here on the far right, I'm going to create that table of coordinate points. So I'm going to stick with negative 2 through 2. I see that the graph is slightly moved over to emphasize quadrant 2. But I think we'll be okay in terms of our y values if we go negative 2, negative 1, 0, 1, and 2 for this quadratic. To calculate the y values, I'm going to bring the function, so it's negative 2x squared plus 4. And let's generate these by plugging these x values in. So it's negative 2 times negative 2 in parentheses squared plus 4. So negative 2 times negative 2, that squared part becomes positive 4 times negative 2 is negative 8 plus 4, which is negative 4. Okay, we keep going. Negative 2 times, in parentheses, negative 1 squared plus 4. Negative 1 squared is negative 1 times negative 1 is positive 1 times negative 2 is negative 2 plus 4 is 2. Always enjoy calculating with 0. 0 is the great destroyer. That whole first term becomes 0 plus 4 is 4. And that seems to be the vertex. Let's see if the y values then decrease from 4. In fact, we're looking for them to match the 2 there. So that is at positive 1. So negative 2 quantity 1 squared plus 4. 1 squared is 1 times negative 2 is negative 2 plus 4 is 2. So we do see that patterning. I expect this next value to be negative 4 based on that symmetry. Negative 2 times positive 2 squared plus 4. 2 squared is 4 times negative 2 is negative 8 plus 4 is negative 4. And indeed, that shows that symmetry we expect with quadratics. This is a downward opening parabola. Let's graph it. So negative 2, negative 4. Negative 1, positive 2. We can see that vertical stretch from this coefficient of 2. 0, 4. And then we see that symmetry in the graph as well. So I'm going to graph this parabola. It's downward opening with its vertex there. Let me put that through the points at the y-axis at 4. So there we've got a rough sketch of the quadratic. Now, to confirm that our tangent line really does hit this graph just at the 1 point, negative 1, 2, I want to graph the green one, y equals 4x plus 6. So recall the way that we graph slope-intercept lines. We start with the b value, which in this case is 6. You plot that on the y-axis, and then I'm going to use the slope. I'll assume it's 4 over 1 so that I get the rise and the run. So I'm going to rise 4 to 10 and run to the right 1. And that takes care of that upper direction. We can do the same equivalent slope by decreasing by 4, running to the left 1. That's still positive slope. So 6 down 4 is to 2, to the left 1. So it does go through our point negative 1, 2. I continue the pattern down 4 to negative 2 over 1. I can see it's not intersecting the graph there, so that's good. It's a tangent line. And then that's emphasized as that decreases. So here's the graph of our tangent. And that completes that process. So just again to recap, we use the limiting process using the idea of slope of a secant line to find the slope of our tangent line. That's in the purple there. We grabbed the original point as our x1, y1 and our slope of the tangent line to write the slope-intercept equation. Notice we started with point slope form, and then we used a table to graph the original function, and then placed our tangent line on the graph to confirm that it is in fact tangent to the graph at the point negative 1, 2. Let's take a look at our second example. So in calculus, we really focus on tangent lines. We also focus on what we call normal lines. Just to give a technical definition, a normal line is a line that's perpendicular to the graph at a given point. Tangent, we think it's parallel to the graph at a given point. It's the exact same slope of the function at a point. What we're saying with a normal line is its slope is perpendicular to the slope of the function at a given point. So let's take a look at this example. We'll give our 100% here so we can read. So here our function is different. It's not a quadratic. So our f at x here is a radical function. Y equals parentheses negative 2x plus 4 to the power of half. I'm going to label that as f of x. And then I've got this point, so it's good to label stuff as we begin. 0, 2 is my C, F at C. So notice we want to start by finding the slope of the tangent line. So the general strategy here is I'm going to find the slope of the tangent line and then use the geometric principle of negative reciprocal to write the slope of the normal line. Remember, a line that's perpendicular has a slope that's the negative reciprocal of the original. And then our other strategies will be the same. So there's just that one change here in terms of the slope. So let's write f prime at C here is at 0. So again, that's the notation for the slope of a tangent line, equals the limit as x approaches my C value of 0 of the fraction f at x in the numerator, so that's negative 2x plus 4 to the power of 1/2 minus my f at C value is 2 over x minus C, in this case, 0. So we want to take that limit. Again, what we're interested in is a definite numerical value. One thing that I need to remember is that this power of half is really a square root. So just to kind of capture a way to deal with this limit, I'm going to rewrite this initially as the limit as x approaches 0 of not power of a half, but the square root of negative 2x plus 4 minus 2 over simply x. I can let that 0 go. So the question at this time is really, how do I find the limit of an expression that has a radical and it's also a rational function? So remember our strategy. To do this, I'm going to multiply by some terms here on the right. We should check to see if direct substitution would work. If I put in 0 for x, I do get denominator of 0. Let's check in the numerator. If I put 0 in for the x above, that'd be negative 2 times 0 is 0 plus 4. Square root of 4 is 2 minus 2 is also 0. So that confirms direct substitution is going to give us the indeterminate form. So I'm going to back off from that since that won't work. And what I want to remember is the strategy of multiplying by the conjugate. So recall, if I've got this arrangement, a radical plus or minus a number over something, I'm going to multiply by the same radical, so negative 2x plus 4. Notice that didn't change, but the minus outside is going to become plus 2. And remember that we call the conjugate. And then I'm going to put that over itself. So algebraically speaking, I'm just multiplying by the equivalent of 1. And remember, algebraically, 1's the identity, so we're allowed to do so. So now I want to simplify. We've got to use our FOIL, our double distribution. So our first terms as we create this equivalent form of this fraction with a radical is going to be square root of negative 2x plus 4 times itself. So it's the limit as x approaches 0 of square root negative 2x plus 4, and then we could write that as squared. My outer terms are, and I'll put these lines so that we can see what we're multiplying. Outer terms is going to be plus 2 times, in fact, let me use a different color so we see that each of these terms is distinct. Plus 2 times the square root negative 2x plus 4. The inner terms, I'm done with that first term in the purple. Now I'm moving to the negative 2. Those are my inner terms. So that's now going to be negative 2 times square root negative 2x plus 4. And then the last terms, the L in FOIL is going to be -2 times +2, which is -4. So there's our FOIL in the numerator. And recall, this strategy says don't distribute the terms in the denominator in this case. So I'm going to leave it because what I'm looking for ultimately is a cancellation to do a sidestep of that indeterminate form when I do direct substitution. So now I need to simplify. The way we've created this, the outer in the blue and the inner in the red cancel because they're the same term, opposite sign. The other thing that will cancel here is the square and the square root. Those are inverse operations. So if a square root, it cancels both. And that gives me now this simplified version. It's the limit as x approaches 0 of simply -2x plus 4. Notice the square and the square root are vanished. -4 over x times the square root of -2x plus 4 plus 2. I was reading the numerator there, plus 2, and that's in parentheses. So we see a product in the denominator. So what I do at this time is I'm going to notice that I don't need the parentheses in the numerator. And then I've got another cancellation. 4 minus 4 is 0. So now the only term left is -2x. And I see I've got an x factor above, an x factor below. So I'm going to let those cancel. And this is now simply the limit as x approaches 0 of just -2. Look how that numerator is simplified way down over the square root of -2x plus 4 plus 2. So at that point, we're ready to use direct substitution to simplify that limit. So this is now equal to, I'm going to drop the limit notation, and I'm going to just substitute in 0 for x. So it's -2 over the square root of -2 times 0 plus 4 plus 2. And that becomes -2 over this -2 times 0 under the square root becomes 0 plus 4. Square root of 4 is 2. 2 plus 2 is 4. And that reduces to -1/2. So I'll box that. Now I got to interpret that. That is the slope of the tangent line. So if I were writing the equation of the tangent line, I would use -1/2. But recall our strategy here is not to write, or our task really is not to write the equation of the tangent line, it's to write the equation of the normal line. So I'm going to use the tangent line, but I've got to do two things to find the slope of the normal. I need to switch the sign, so negative becomes positive. And then I need to find the reciprocal of the fraction, so half becomes 2 over 1. So the slope of the normal line is just 2. And that's what I'm going to take with me to the bank. I'm going to go now to write the equation of the normal line. So we'll do that now in green here because we've kind of reached the transition point. So again, this is the equation of the normal line. We'll use that same point slope, not the normal line. We'll use that point slope form and fill that in. Just to remember, that's y minus y1 equals m times, in parentheses, x minus x1. So some of these things we already know. The slope of the normal line is 2. And then my x1 and y1 again show up from my point, which we had called c f at c. So the x1 value is 0. The f at c value, or y1, is 2. And then the other parts of the slope, point slope formula, I'm just going to import. Y minus 2 equals 2 times, parentheses, x minus 0. So I just want to simplify that now, get the slope-intercept equation. So the left-hand side we'll deal with later. So that's y minus 2 equals just 2x. And then the only thing to move is this minus 2. So I'll add 2 both sides. And this is really our task complete. This is now y equals 2x plus 2. And I'm going to box that. That is the equation of my normal line. So now we want to graph it. So over here on the side, the far right over here, I'm going to create that table, x, and I'm going to put the function. So I'll write it the way it was normally or originally written. So parentheses negative 2x plus 4 to the power of half. So remember that is the square root. So my x values, let's choose negative 2 through 2. And we'll calculate these y values. So I'm going to substitute in the x value. So it's negative 2 times negative 2 plus 4 to the power of half, or really the square root. So simplifying that, that becomes negative 2 times itself is positive 4 plus 4 is 8. So this is equivalent to the square root of 8. I'm going to get a decimal in a moment, but let me finish calculating these all first. So negative 2, substitute in negative 1. That's negative 2 times negative 1 is positive 2, plus 4 is 6. So this is the square root of 6. Again, I'll get an estimate for that. Third value is negative 2 times 0. That's 0 plus 4. The square root of 4 is exactly 2. That's a solid point. I don't need to estimate that one. Negative 2 times positive 1 plus 4. That's negative 2 times 1 is negative 2 plus 4 is 2. And I'm going to write that as the square root of 2. Negative 2 times positive 2 is negative 4, plus 4 is 0. The square root of 0 is 0. Just out of curiosity, I do want to see what happens when I use the x value of 3. So I'm going to just incorporate another x value there. And I want to see what this output's like. So negative 2 times 3, that's negative 6, plus 4 is negative 2. And recall the square root of a negative value is not defined in the real numbers. That's an imaginary value. So what I'll put here is that's undefined. And that's very typical of square root functions. They terminate at some point in the domain. And then there's a whole region of the domain where they're not defined. And it comes to this very fact that all those values are square roots of negative numbers under the radical. So I want to graph it. Strategy here to get those square root approximations is really to use the calculator. So I'm going to head over to Desmos just to demonstrate what those estimates are. So I'm going to type in that function, f of x equals square root of negative 2x plus 4. So that gives you an idea about what the graph looks like. It opens to the left. It's got its vertex at 0, 2. We actually calculated that point. But I want a table. I said 0, 2. It's 2, 0. Sorry, guys. Convert to table. And those are the estimates. So what I'm going to write down is square root of 8 has about the value of 2.828. Square root of 6 has the value approximately 2.449. And then the square root of 2 has an approximate value 1.414. I do want to see what Desmos says about the output at 3. So it does say undefined. And if I keep going, lots of undefined terms there. So that's everything to the right of 2. All right, so calculator is very helpful in terms of making estimates efficient. We want to graph. So I'm just going to write these estimates down. Square root of 8 was about 2.828. Square root of 6 is roughly 2.449. And then the other one I want to estimate square root of 1, 1.414. So I'm going to graph on the coordinate plane this function first. So it's -2, -2.8, so almost at 3. -1's pretty close there. It's just about 2.449, 2.45. 0 is exactly at 2, so that's the y-intercept. 1 is 1.414, that's the estimate of square root of 2, and then 2 zeros there, that's the vertex. So I'm going to graph this function. It opens to the left. I'm going to start on the left, get a better curve. The left-hand side is infinite. The right-hand side is finite. Now, let's graph our green line here, the normal line, at the point 0, 2. So I see from my equation y equals 2x plus 2. The y-intercept there is 2. And then the slope is 2, so I'll graph that as 2 over 1. So up 2 over 1, that's the point 1, 4, 2, 6, 3, 8, 4, 10. And then I can reverse from the y-intercept down to left 1. That's -1, 0, -2, -2, -3, -4, -4, -6. And what I'm checking for is, does this line appear to be perpendicular to the graph at that point? And it looks almost like an arrow stringed onto a bow. And it certainly is perpendicular. Thank you for joining for this investigation of writing equations of tangent lines and normal lines to curves at certain points. I'm going to let you go work on some of your problems. Thank you for joining. See you soon.